Okay, here's an example problem of propagation, and in this problem we're comparing wireless propagation to wired propagation. And what we're going to see is that in the wireless world we're going at a speed of 3 times 10 to the 8th meters per second, where on copper wire we're only going at 2 times 10 to the 8th meters per second. And we'll see that there's a difference in propagation time in this example down the hallway, 14 meters down the hallway from the access point to your laptop. Okay, and so part A asks you to calculate the length of time needed for the signal to travel 14 meters through the air down the hallway from the access point to your laptop, giving the answer in nanoseconds. And what we're going to do is we're going to use the equation the distance is velocity times time, and we're going to use the fact that the velocity is the speed of light in air. In fact, this wireless signal, which is a radio wave, goes at the speed of light in a vacuum, but in air here on the surface of the Earth, it's 99.9% of the speed of light. So we're just going to go ahead and take it to be the speed of light, and we're going to go 3.0 times 10 to the 8th meters per second. That's the speed of light, basically. Okay, and it wants us to calculate the time, and so we're going to solve this equation for t. T is equal to the distance divided by the velocity, or the distance divided by c. And the distance is 14 meters, and c is 3 times 10 to the 8th meters per second. And you can see that the meters cancel in the units here, and seconds in the denominator of the denominator become seconds in the numerator, and that's the units on time t. So if I plug this into my calculator, I take 14 divided by 3 times 10 to the 8th equals, I get 4.7. Let's see, can I put it in engineering notation? Okay, I get 1, 2, 3, 4, 5, 6, 7, 8. 4.7 times 10 to the minus 8 seconds. Okay. But this says to put the answer into nanoseconds, and a nanosecond is 10 to the minus 9th seconds. And so here we have 4.7 times 10 to the minus 8th. 10 to the minus 9th is a smaller unit. So if I'm going to go to a smaller number here, I better go to a larger number by the same number of places, and it's going to be 47 times 10 to the minus 9th seconds, or 47 nanoseconds. Okay, that's part A. And once you figure that out, part B is essentially just the same with different numbers. T is D over C. Oh, I'm sorry. Now we use a different velocity, V, and we're going to plug in 14 meters. So our new velocity is 2 times 10 to the 8th meters per second. And we don't label that as c because c is reserved for the speed of light. Okay. And notice that I'm showing all the work here. I'm showing the equation I'm plugging into. I'm showing the numbers that I'm plugging in. 14 divided by 2 times 10 to the 8th equals, and I really do have to figure out how to put this into exponential notation on this calculator. I think I figured it out. I get 7 times 10 to the minus 8th. Oh, 14 divided by 2 is 7, and 10 to the 8th in the denominator becomes 10 to the minus 8th in the numerator. I didn't need a calculator for that one at all. And this is 70 nanoseconds then. by the same logic I used before. And so it takes longer because it was going slower. Okay? And part C says if there were a race, which one would win? The wireless wins over the copper. And I'll at least try to make my work legible. The delta t, the change in the time, the amount by which wireless wins the race is 70 minus 47 nanoseconds, which is 23 nanoseconds. Okay, so wireless wins the race by 23 nanoseconds. In fact, nanoseconds are imperceptible to humans, and as far as we're concerned, they're both instantaneous. Okay, hope that helps.